And we see the color-coded areas, the metals, the semi-metalloids, and the nonmetals. So we talked a little bit about that. The staircase thing works pretty well, although we usually lump aluminum in with the metals rather than the semi-metals just because it has more metallic properties. Now, there are some other names that we give these columns that you see here. Group 7, the halogens, group 8, the noble gases. Any idea why these names always go in columns? Or what things with special names have in common? Where those, not necessarily names come from, but why do we care about lumping things with this name in a particular column? Yeah, exactly. They have these properties. And in fact, that's true for the entire periodic table, that things in a column, elements in a column, are going to have some similar properties and similar chemical behavior. So they're going to react with other molecules in a somewhat predictable way. In fact, that's the whole name, periodic table. Periodic means cyclical or in a cycle. So as we go from left to right, those are called periods. So you kind of, when you start at lithium, you go through all these elements, you come back in A, you have something that's similar to lithium. You go to Mg, something that's similar to beryllium, Be. So you have this cyclical nature table, and the reason it's laid out is that it's in the same similar properties. All right. The reason for that, where that comes from, comes back to the electrons. As we'll learn in a couple chapters, well, I guess in the chapter after this one, chemistry is determined by electrons. It's determined by electrons from one atom interacting with from another atom. And so we care very much about what the electrons do. In fact, so much that we're going to pretty much stop caring about what the nucleus is doing. So it's good. We want to know protons. We want to know how many neutrons. Great. That doesn't really affect the chemistry. Different isotopes of a similar element, like carbon-12, carbon-13, actually react about the same way, form the same kinds of compounds, do the same kinds of things. So when we talk about chemistry, we're really concerned with the electrons. And so we're going to look at the configuration of the ions in an atom. Okay. To do that, you need to remember 3 numbers. You can remember those? What? I don't want to memory. Okay. All right. You know what? Say it. Close it and let this other program to save memory. And we'll close this one too. All right. So these are the numbers of electrons that fit in each level outside the nucleus. So the old model of the atom is that you have a nucleus in the middle and you have electrons that orbit around it. You've heard that or kind of seen pictures of that. That doesn't reflect reality. That's called the Bohr model, and that was sort of the original idea of what an atom looked like. It's not real. A better description is you have a nucleus and then the electrons in clouds outside of the nucleus. Some clouds are closer, some clouds are further away. And the further they get away, the higher they get in energy, meaning the less stable they get, meaning the more they can go do stuff with other atoms. So we care mostly about the electrons that are furthest away from the nucleus, that aren't being held in quite as tightly from the nucleus. And to find that, we use these numbers. So if we start hydrogen, we're going to draw a little graph where we've got energy on the y-axis. And how many electrons does a neutral hydrogen have? 1. Make a little bucket, a low energy bucket, and we're going to put 1 electron in it. Not exciting so far. We'll get a little more exciting in a minute. Let's do helium, the next one. Same deal. We got our bucket. How many electrons in a helium atom? Two, because the protons are 2, it's neutral, so 2 electrons. That little e with a negative sign is a symbol for an electron. We put 2 in the bucket. Now that level only holds 2. That's its total capacity. So that's the first level, second, third. Those of you who have taken more chemistry know that there's actually it gets a little more complicated in the third level. We're not going to get into that in this class. So we'll say that the first level is full now with helium. So when we go to lithium, the next one on the list, 3 electrons. We're going to make the same bucket for 2. We're going to run out of space in that bucket because it can only hold 2. So we put in another one that's a little bit higher energy, meaning that those electrons are now a little bit farther away from the nucleus. And this bucket's a little bigger and holds 8 electrons. 1, 2, and we put the third one in there. Maybe not. Let's skip a few. Let's skip a few and try another one. So let's look at what happens when we get to sodium, Na. How many electrons does sodium have? 11. A neutral atom is always going to have the same as the atomic number, the number of protons. So we'll set up our buckets again. There's our 2 and there's our 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we need another bucket for one more. So the third is going to be even higher energy. We'll put our last electron in there. And the chemistry that these can do, or the reactions they can do, say occurs. We spell it right. Chemistry occurs at the outer, or the highest bucket. It's furthest away from the nucleus at the highest energy with the least amount of pull and attraction. And there's a name for that. Anybody know what that name is? Yeah, that's called the valence. The valence electrons, or the valence shell, or the valence level, are those ones that are furthest from the nucleus, and they're responsible for the chemistry that element or that atom can do. The reactions it can do, the compounds it can make, all that kind of stuff. Their properties. So when we look at the electron configuration of an element, we want to know how many electrons does it have in that valence shell, how many in the outermost bucket. And we can count that pretty easily. Like in sodium, how many valence electrons does it have? Just 1. So that's our valence electron. And then all of the other ones are called core electrons. So toward the middle, not in the valence. How many valence electrons does lithium have? 1. So 1 valence electron, 2 core electrons. How many valence electrons does hydrogen have? We'll skip helium for a minute. 1.
So those are the only ones that can bond or interact with other.
Right. Now, if you look at that, you see, okay, hydrogen, lithium, and sodium all have 1 valence electron. And if valence electrons are what dictate some things about the chemistry, then we would expect that those have some similar behavior. And then if we look at the periodic table, we notice that those are all in a line also. Now look at the number on top of the column. That column is known as group 1A, or sometimes just 1, depending on the numbering system. What do you think that 1 might refer to? Yeah, the valence electrons. So we can actually use those numbers across the top as a shortcut to finding the number of valence electrons. Helium's, yeah. In fact, all the other ones in that column have 8 valence electrons, but helium doesn't have enough space, so I guess that's where it doesn't work. Just for helium, because it only can get 2.
Even though it shows, even though it has 2.
Yeah, so helium has 2 valence electrons, even though it's in column 8. Yeah. But let's check it for something like, let's say sulfur, S, number 16. We got 1 more minute we can do. So sulfur has 16 electrons. And how many valence electrons do we get to have based on the periodic table? Just in the valence, though. If we look at those column numbers, 6, because it's in 6A. So let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So how many electrons in that outermost bucket? 6, as we predicted. Sulfur has 6.
How would you be able to determine that? Because I mean, obviously we have a periodic table that tells you how many valence.
Yeah. Well, you need the other. You either need a periodic table, or you need buckets. You need to know how big the buckets are, and you can count them up one by one.
This is saying how we know what goes in.
You start from the bottom. You put the 2 in the bottom one first, then you go to the next one with 8, and then when that one gets full, you go to the next one with 8.
This only goes up to 8. The second one?
Right. Right. You only go up to 8.
So what about the
Well, yeah, those get a little more complicated.
Yeah,
so it's the same idea. Actually, all the ones in the middle, called the transition metals, the ones with D's on the column, they don't quite work as nicely with this. They have some other things going on, and we won't really get into that. But actually, even the late numbers will still work. The problem is they can't be counted out this way. So if you look way down at something like bromine, number 35, bromine does have 7 valence electrons. You can use the column to figure that out, but you can't count them out with the 2, 8, and 8 because you run out of buckets and then it gets a little more complicated. The higher buckets get more complicated. If you want to know about it, I'd be happy to tell you about it sometime, but it's considered beyond the scope of this class.